Hello everybody, it is Mr. Canfield. Today we start the last topic in Book 1, Chapter 24, Indeterminate Forms and LH Hospital's rule. We'll talk more about that later, and the correct pronunciation of it. Anyway, so we're going to go back to the beginning of the year and talk about limits. Yeah, aren't you happy about that? Limits, ooh. So I just want to remind you, if we had a limit that said something like limit as x goes to 2 of x minus 2 over x squared minus 4, the way that we would handle this before is we would first try direct substitution, which literally just meant, hey, plug the 2 in. If we do that, we get 2 minus 2 over 2 squared minus 4, which turns out to be 0 over 0. And we were all like, wah. That doesn't tell me anything. I'm supposed to get some kind of number, but 0 over 0 is not some kind of number, and it's also not some kind of asymptote. Turns out this was a removable discontinuity when x was equal to 2. The way that we would handle this is we would go, oh yeah, the bottom is factorable. We could say x plus 2 times x minus 2. When we do that, and then we plug in the 2, we have 1 over x plus 2, and we can plug in the 2 and get 1 over 2 plus 2 and get 1/4. And we were all like, yeah, got it. So the other kind that we had, limit as x goes to infinity of 1 minus 4x minus 5x squared over 3x squared minus x minus 4. The basic idea with this was if we're going out to infinity and we're plugging in infinity to this, infinities are different sizes, and the infinities that we care about are the greatest infinities on the top and the bottom. 1, not infinity, so it's basically not going to matter as we go out to infinity. Then we got 4x, so that's 4 infinities, but this is 5 infinities squared. Infinity squared makes regular infinity look like a baby, and it's invisible, so it's gone. Same thing with the 4 down here and the regular x down here. The only thing that really matters is the negative 5x squared over the 3x squared. This is a very informal way of talking about this, but it's the same idea of finding our horizontal asymptotes, and we just look for the biggest powers of x on the top and bottom, and oh wait, negative 5x squared over 3, this approaches negative 5/3. And I just want to remind you, this never actually equals negative 5/3. There are these little extra things tacked onto the top and bottom that do get it a little bit away, but like 5.0000000, like it's this kind of business. You know, we're going to be out somewhere, and it's going to like basically be negative 5/3, and then as we reach infinity, which you never actually reach infinity, Buzz Lightyear, because of that, if we were to ever actually reach infinity, we would get negative 5/3 exactly. So, but that's inappropriate to say that we ever would reach infinity, so I'm fired. All right, so we have a few different indeterminate forms that I want to draw your attention to. The first indeterminate form that we have is 0 times infinity. 0 times infinity. And the reason this is indeterminate, that it's not just 0, is that this is the limit. They're both approaching these. The thing is, the one that's approaching 0 might not be approaching 0 fast enough, and so the infinity might actually drag it up from the depths and bring it up to infinity. So this actually could be 0, it could be infinity. There's a lot of things that could happen. It could even be a number. And I like the little conflicts that he has listed here. He says the conflict here is that 0 times anything is 0. But then we've also talked about how infinity times anything is infinity. And so, you know, this is the classic, an immovable object and an unstoppable force collide. What happens? So here's another one. Take any number minus itself and you get 0. But infinity is not a number, so what happens when we take infinity minus infinity? And then another one, 1 to any power is 1, however, a number to the infinitieth power is infinity. 1 to the infinity is another strange one, and 0 to the 0 is another one. Traditionally, we say 0 to the 0 is undefined, but if that is the limit, then maybe something's happening there. And the last one that we have, infinity to the 0 power, is not necessarily 1. So these are all called indeterminate. So let's break this word down. The root word here is determine. You know what the word determine means. Can we determine this? Can we determine that? Determinate just means like determinable. It's the suffix undetermined to make it able. So instead of saying determinable, we say determinate. And then we have the prefix in, which means inside. No, just kidding. It means not. So not determinable, not find outable is how I like to say it. And so any of these forms on their own, if we get them, this means I need more information. It doesn't mean it's over. It means I need more information. So I am going to need to resort to history for a moment. We're going to call on the power of a man from the 1600s. Here he is. Bonjour, je m'appelle Guillaume L'Hôpital. And that's the extent of the French that I'm going to use on that. His name is Guillaume L'Hôpital. It means William L'Hôpital. So yeah, we pronounce it L'Hôpital. Just say low and then say pit and then talk about your friend Al L'Hôpital. But it's not spelled like that. French is funny and has lots of additional letters even though you don't pronounce them. So one way that we pronounce it is El Hospital. If you ever call it El Hospital, your math teacher will punch you. I mean, your math professor will punch you. I will not punch you because I will just, help you remember that in French, this S is silent, as well as the H, because of course it is. It's French. Another spelling, and this is my preferred spelling because I love fun letters. Boop, boop. We got that one. So, forgot the L. So this O, I think it's L'Hôpital. But anyway, you can call him L'Hôpital because we're in America, and in America we say things poorly. So L'Hôpital or L'Hôpital. Anyway, I like the picture because his hair's amazing. Don't you wish that you had hair like this? I know it's a wig. Don't you wish you had a wig like this? Puts weave to shame. All right. So, okay. Not really. I think weave's wonderful. Okay. So, the problem with L'Hôpital is that we can't just say, hey, I'm just going to invite my friend L'Hôpital over and he's going to do all the work for me. There are certain things that we need to be able to invite him over, and those are very specific. You either need to have 0 over 0 as your limit, or some form of infinity over infinity. It's plus or minus. It really could be any kind of positive or negative infinity over infinity. One of these cases means that, hey, we're allowed to use our buddy L'Hôpital. And the reason why I'm calling him our buddy is because you're going to love it. I'm going to go back to that old limit we did a minute ago, that x over 2, and then, x minus 2, and then x squared minus 4, the limit as x goes to 2. So remember how we plugged it in and we had to factor and do stuff? And this is an easy example. We had to factor and do stuff and then replug it in. Check this out. L'Hôpital goes and he figures this rule out. When we plugged it in, we got 0 over 0. That's our clue that we can use him. Oh, 0 over 0, you can use it. Hooray! Okay, so here's L'Hôpital's rule. What's the derivative of the top? 1. What's the derivative of the bottom? 2x. Now, plug the 2 in. What do you get? 1/4. Guess what? It's the same limit. It's the same answer. So, I had to pick this up off the floor. Instead of, after we get 0 over 0, factoring, canceling, doing stuff. Ooh, I got the number. We got to derivative, answer. Let's do one more. Let's look at the, where is it? Let's see. It was 1 minus 4x minus 5x squared all over 3x squared minus x minus 4. The limit as x goes to infinity. All right, so even on this one, if I plug it in, on the top we get 1 minus infinity over infinity minus infinity. We get infinity on top, infinity on the bottom. Lots of infinities. L'Hopital's rule goes, oh, wait. We got infinity over infinity. Hello. All right, so we can use, wait, no. Bonjour. That's what I was supposed to say, right? Because he's French. Okay, so we take the derivative of the top. We get negative 4 minus 10x over 6x minus 1. Plug in infinity now. Oh. I got infinity over infinity again. L'Hopital goes, bonjour, and we can do it again. And then we take the derivative of the top, we get negative 10. We take the derivative of the bottom, we get 6. This goes to negative 5 over 3. Now, if you can do this one in your head and you understand how this works, that's great. And that's awesome that we got negative 5/3. But this, doing L'Hopital's rule, is a way for us to get that number if we're not sure what's happening. So we're going to do a bunch of examples of this. And generally speaking, notes like this will have example after example where L'Hopital's rule is applied. I always do the check because there's always the possibility that his rule is not applicable. So I start out in example number 1, 3x squared. Good job writing a squared, Canfield. Minus 7x plus 2 over x minus 2. All right, so if I plug in 2, it's the limit as x goes to 2, sorry. So I got a 0 on the bottom, then let's see, 3 times 4 is 12 minus 14 plus 2. Yep, I got 0 on the top. Okay, 0 over 0. Bonjour! And so because of that, I can take the derivative of the top and bottom, 6x minus 7 over 1, plug in the 2, and we get 12 minus 7 over 1, we get 5. So instead of having to factor the top and then do canceling and then plugging in the 2, our buddy L'Hopital lets us just jump right to the answer. Let's look at number 2. Number 2 says the limit as x goes to negative 3 of x plus 3, and then x squared minus 5 minus 2. All right, let's see. So if I plug the negative 3 in, I get 0 on the top. On the bottom, I get, well, negative 3 squared is 9, so 9 minus 5. Square root of that's going to be 2 minus 2. We do get 2 minus 2, we get 0 over 0. Whoosh. Bonjour! All right, remember, we can only use him if we get 0 over 0, or infinity over infinity. So derivative of the top is easy, 1. Derivative of the bottom, remember, we have an x squared, or sorry, a square root of x thing here. So square root of x things always turn into 1 over 2 root the stuff. And then we just got to make sure we multiply by the derivative of the inside, which is a 2x. So I'm going to do times 2x on the top. The 2 turns into a 0. And you might be like, this looks terrible. Yeah, just give it a second, okay? There's a 1 up here. You know that 1 just means reciprocal of whatever. Like if it's 1 over something, it's a reciprocal of this. But if I plug in negative 3, I'll get a negative 6 on top, 2 root. Oh, this is going to be the same as it was before, right? 9 minus 5. So this is just going to be square root of 4, which is 2. So I could rewrite this as 1 over negative 6 over 4, which just flip it, and we get negative 4 over 6, or negative 2/3. So there is a technique to do this without taking the derivative, but it involves something called conjugation. And you might not remember conjugation from pre-calc, and we did not spend a lot of time on it this year. All right, let's see. Number 3, oh, big polynomial. The limit as x goes to negative 2 of x cubed plus x squared minus 8x minus 12 all over x cubed plus 8x squared plus 20x plus 16. All right. So let's see. I'll plug in the negative 2, and you need to do this. There's no way to know what this limit's going to be. Maybe you can see the future and you already know what it's going to be. Let's see, negative 8, then plus 4, then plus 16, then minus 12. Is that even 0? See, those are 20, and those are negative 20. So yeah, the top is 0. The Let's look at the bottom. We get negative 8 again, plus 32 minus 40 plus 16. Let's see, that's negative 48, that's positive 48. It is 0 over 0. Bonjour! All right, so that means that we can take the derivative of the top and bottom, and I get 3x squared plus 2x minus 8 all over 3x squared plus 16x plus 20. And now I got to plug in negative 2 again. And let's just pause really quick. Something that you might be noticing is we're kind of doing something different than what we would normally do with derivatives. If I was taking the derivative of the whole thing, I'd have to do quotient rule. We're not doing that. L'Hopital's rule lets us take the derivative of the top and bottom separately to do a limit. This is not to be confused with what we normally do in derivatives. All right, let's see. Plug in the negative 2. That's 3 times 4, which is 12. Minus 4 minus 8. Oh, the top is 0. Then on the bottom, 3 times 4 is 12 again. Minus 32 plus 20. Oh, we get 0 over 0. And so all we have to do is redo L'Hopital's rule. Oh, wait, I'm sorry. Bonjour. Okay, so if we do L'Hopital's rule again, we'll get 6x plus 2 over 6x plus 16. Now let's see what happens when we plug in negative 2. I get negative 12 plus 2 over negative 12 plus 16. Cool, I get a number now. I get negative 10 over 4, which is negative 5 over 2. So not something that you would immediately grab from here, and just looking at it personally, I don't see, I'm not seeing any ways that I would know how to factor this. If you do, feel free to leave a comment about it or let me know in person. But we go from something essentially undoable to this. Oh, I remember how the way that you would do this is you would use synthetic division to divide this out of the top and the bottom, and then like try to cancel it or something. Is that what we would do? Whatevs. We don't need to do it because we got L'Hopital's rule. So it makes him so great. I'm talking about it like the rule is him. It's not. He's more than just a rule. Oh no, I was going to write the limit as the limit. The limit as x goes to 1. Let's see. All right. So I plug in some 1s. Let's see what we get. 1 minus 2 plus 1. Oh, surprise, it's 0. Then on the bottom, 1 minus 3 plus 3 minus 1. Oh, it's 0. Bonjour. And if you're wondering why I'm not saying bonjour or bonjour, it's because anyway, French. All right, let's see. So we'll take the derivative of the top and the bottom using L'Hopital's rule. So we get 3x squared minus 4x plus 1 over 3x squared minus 6x plus 3. Darn. I was hoping it would be a number now, but instead, we get 3 minus 4 plus 1 over 3 minus 6 plus 3. We wind up getting 0 over 0. You know what I'm going to say. Okay. So L'Hopital says, let's take the derivatives again. We get 6x minus 4 over 6x minus 6. Uh-oh. Did I make a mistake? Because right now I get two over 0. And he looks at this and he's like, it's not 0 over 0, it's not infinity over infinity. I can't do anything with this. So, just pause real quick. Sorry about that, I'm back. So what we're going to have to do now is take the limit of this. Since it's not 0, 0, we're going to have to do some kind of asymptote analysis here. So we know that we have 6x minus 4 and we have 6x minus 6. And if we kind of look at a sign chart here, we're looking at it as x goes to 1. So if I try 1, we have a D and E situation. We're trying to find out, does it go off to positive or negative infinity on either side? And does it do the same? So if I try something less than 1, ever so slightly less than 1, this is where the numbers actually do matter. So like I would want to try something like 0.99999999999. Like we want to try something really close to 1. This one's simpler to see. 6 times not quite 1 minus 6. The 6 is going to be bigger, and so we're going to get a negative. But here, this is essentially 6 minus 4, which is going to be a positive. And so on this side, it's going to be going off to a negative infinity. And on the right-hand side, if we look at this, let's see, if we try a number ever so slightly greater than 1, we wind up getting a positive number still here. And now we wind up getting a positive, we wind up going off to positive infinity. So we can say that this limit does not exist. So I'm just going to double check one more thing. All right, back again. So I was just double checking because Stu in his work said it goes to positive infinity, but according to this, it goes to neither because it's going to both. And I just double checked with a computer system that agrees with me. So regardless, what we were able to do was, since we got 0 over 0, we got 0 over 0 again when we took the derivatives. The third time we took the derivatives, we did not get 0 over 0. If you continue to use L'Hopital's rule here, and, so we got DNE. If you continue to use L'Hopital's rule and do it again, you wind up getting 6 over 6, which is 1, which is not true. And that makes L'Hopital very sad, because he looked at that and he said, I can't use that. So don't just try to use him anytime you can, or anytime you want to. You can only use him when you get 0 over 0, infinity over infinity. Don't abuse him, use him correctly. All right, number 5. 5 says cosine of x minus 1 over x squared minus x. X is going to 0. So I'll tell you right now, top is 1 minus 1, which is 0, bottom is 0. So it's 0 over 0. Cool. Let's take the derivative. I get negative sine of x over 2x minus 1. You might be thinking, oh, I get 0 over 0 again. I got to use L'Hopital's again. Pause. Plug in the 0. We get negative sine of 0 over 2 times 0 minus 1. Oh, snap. 0 over negative 1. It's 0. The limit is 0. So only had to use L'Hopital's once because then we were able to plug it in and get the answer. All right. Number 6. 6 says the limit as x approaches 1 of the natural log of x minus x plus 1 over e to the x minus e times x. All right. Plugging in 1. Remember that the natural log of 1 is 0. So that's 0 minus 1 plus 1. We get 0 on the top. The bottom we get e to the 1, which is e, minus e times 1, which is e. E minus e is 0 as well, so 0 over 0. Bonjour. Why did you not ask me last problem? We didn't ask him the last problem. I shouldn't try to do a French accent. I can't. All right. So I'm allowed to use L'Hopital's rule. So I can say 1 over x minus 1 over e to the x. Now careful here. This is e times x. So the derivative of this is going to be, this is a number times x. The derivative of a number times x is just that number. So it's minus e. So now when I plug it in, I get 1 over 1 minus 1. E to the 1 minus e. It's 0 over 0. Bonjour. So we use them again. Now we got to take this derivative. We're going to get 1 over x. Remember, we'll use our buddy Happy Hair Pen. So this is x to the negative 1. So its derivative is going to be negative 1 over x squared, right? It's going to be negative 1 times x to the negative 2, which flips down there. So I'm going to have negative 1 over x squared that 1 goes away. And then on the bottom, we have e to the x. Then the e dies. So now that we have that, we can plug in the 1 again and get negative 1 over 1, and then e to the 1. So we get negative 1 over e is our answer. So cool. We got 3 more, and that's the end of these notes. That's the end of where Calc 1 goes with this. Calc 2, we learn more about this and we learn some advanced techniques, but you just need to understand. Oh, this says sine 2x, like this parentheses is implied on that. All right, so let's see if we are allowed to use L'Hopital's rule here. So plug in 0 on the top, I get 0 minus 0. On the bottom, I get 0 minus 0 times 1. Did you say 0 over 0? Bonjour! All right, so we'll take the derivative of the top and bottom. That's going to be 2 cosine x minus 2 cosine 2x. Remember, we take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. Then on the bottom, we got cosine of x minus, we get to do product rule here. So I'm going to open up a big parentheses because there's this minus sign out in front. So the derivative of our x will be 1. We'll leave the cosine alone. Then we'll leave the x alone. The derivative of that's going to be negative sine x. All right, so we need to be careful right now. There's a lot of moving parts here. So we get 2 cosine, wait, I should write this off to the side. I think it's going to be 0 over 0 again. We get 2 cosine, so that's going to be 2 minus 2 cosine 2x, plugging in 0, it's still going to be 2. Oh, the top's going to be 0. The bottom is going to be 1 minus, well, 1 times cosine, that's 1 times 1 plus 0, because it's going to be 0 times who cares. So we get 0 over 0. L'Hopital comes in and he goes, no. He doesn't want to do this. So 0 over 0, we can apply him, but he doesn't want to work yet. Okay, L'Hopital, hold on just a second. Let's clean this up, and then I'll call you back. Let's see, 2 cosine x minus 2 cosine 2x. Down here, if I distribute the negative, I get minus cosine x, because that 1 cosine is fine. This is a negative x sine x, right? So when I distribute the negative to it, it's going to be plus x sine x. Wait, hold up. So this is cosine x minus cosine x plus x sine x. Oh, that's way better than I thought it was. Those cancel. This is just x sine x. And sure enough, we'll still get 0 over 0. Bonjour! Yeah, he's happier with that. Okay. See, this is what happens when you discover something important. Hundreds of years after you die, people make fun of your haircut. So let's see. We'll take the derivatives again. We'll get negative 2 sine x, and then plus, because it's going to turn into a negative sign. And the 2 is going to pop out, so 4 sine 2x all over. And I got to do product rule again. So I'll have 1 sine x plus, plus x cosine x. All right, I'm hoping this is it. Sometimes we have to go to the hospital go to the L'Hopital a whole bunch of times. So I'll plug in 0, and I'll get, 0 plus 0 over 0 plus 0. I get zeros again. You thought you were done with me. Ha ha ha. All right, there's the saucy French accent. Okay, so we get 0 over 0 again. We got to do L'Hopital's rule again. So we get negative 2 cosine x plus 8 cosine 2x. This has to be the time. We get cosine x, because this time we didn't even have stuff canceling. So we get cosine x plus 1 cosine x minus x sine x. And now when we plug in 0, that's 0. This is 1 plus 1, so the bottom is 2. The top is negative 2 plus 8. We get 6 over 2, we get 3. So we get that nice little happy face. All right. This is, so let's see, we had to do L'Hopital's rule 1 time, 2 time, 3 time, 4. We had L'Hopital was a 4 time and, so we had to do a whole bunch of times. All right, these last 2 are infinity over infinity. So we've really already looked at these, but I'm just going to remind you in number 8, write it so that people can see. Number 8, it says 1 minus 4x minus 5x squared over 3x squared minus x minus 4. So as x is going off to infinity here, I don't need to use L'Hopital's rule. It's negative 5/3. Oh, I actually did this exact same example earlier. So now let's look at number 9. Number 9 is not as straightforward. So number 9 says I'll use that. The limit as x is going to infinity of 4x squared minus 5x plus 2 all over e to the 5x plus ln x. Okay, so problem. Top goes to infinity, bottom goes to infinity, but I don't have exponents this time. I've got e to the 5x, and we haven't really talked about how e to the x compares to x squared. That's more next year too. So we'll take a derivative. We get infinity over infinity. Sorry, I gotta keep doing the silliness. Bonjour. So we'll get 8x minus 5 over 5 e to the 5x plus 1 over x. And now when I plug in infinity, I still get infinity here, and then I get 5 e to the infinity plus 1 over, wait, what's 1 over infinity? 0. But it's still infinity over infinity. Bonjour. And then take the derivative again. We get 8 over 25 e to the 5x minus 1 over x squared, right? Because this is x to the negative 1, and then multiply, and then change subtract 1 from the exponent. So now when we plug in infinity, we get 8 over 25 e to the infinity minus 0, right? 1 over infinity squared is still going to be 0. 8 over infinity. There's no canceling that happens just because they're the same shape, just one's turned on their side. This is actually 0. And that is the AB version of L'Hopital's rule, basically in the depth that you could possibly need for the AP exam. So, hope this was helpful. Au revoir!